Welcome back to section 4 of chapter 8. In this section, we're going to be looking at modeling with quadratic functions. Now, modeling again is when we take real world type situations and we match functions to it to describe what's happening. Our learning targets today: I can use quadratic functions to model real world situations. Now, we did modeling with linear functions way back in first semester. We're going to do the same thing, only with quadratic functions this time. So we have a few different things. Modeling area. Quadratic functions are very useful when modeling area because area is something times something else, generally speaking. So it ends up being quadratic. The units are square units. Quadratic is something squared. So if we want to model this one, we have a company offers rectangular pool sizes with dimensions as shown. So we have 2x and we have x. Each pool includes a deck around it. If Carolina wants a 15-foot wide pool with a deck, how many square feet will she need to have available in her yard? So the very first thing we're going to need to do is let's make a quadratic model. So right now we have 2x and x. That's the size of the pool. We don't want the size of the pool, though. We need the size of the space that she needs in her yard. So this isn't just 2x, it's 2x, and then we're going to add 4 on either side of it. So this will be 2x plus 8. And then the height, it's not actually a height because it's in the ground. I'd call it the depth, but that means something else with a pool. But this side length is going to be x, plus we have another 4 on each side, so this will be x plus 8. So our model, the area, we would have to multiply those together. 2x plus 8 times x plus 8. So that's going to be the area. We can multiply this out. We take the 2x times the x is going to be 2x squared. 2x times the 8 is going to be plus 16x. 8 times x is plus 8x. And then 8 times 8 is plus 64. We can combine our like terms. We have 2x squared plus 16x plus 8x is 24x plus 64. So that would be our model. Now the question says Carolina wants a 15-foot wide pool with a deck. How many square feet will she need to have available in her yard? So wide, let's go, I would say that this long distance is going to be the length. That long distance is the length, which means that this distance would be the width. And so x would just equal 15. We need to plug 15 in here. So we'll have 2 times 15 squared plus 24 times 15 plus 64. 15 squared is 225. So the area would be 2 times 225 is going to be 450 plus 24 times 15 is 360 plus 64. Add these all together. We have 450 plus 360 plus 64. It's going to give us 874. So we need 874 square feet in her yard to be able to fit the pool. So, again, to model, we just multiplied length and width. One of the big mistakes in this type of problem is forgetting the plus 8, or just putting plus 4 because you forget one side. Remember, we need to add the border for each side. Other types of problems very similar to this are going to be a piece of paper with a margin, a picture with a frame on it. Those are very common problems that are of this type. Next type, modeling vertical motion. So vertical motion is always quadratic because of how gravity works. Gravity is an acceleration, or it's an acceleration due to gravity, which means that as you fall, your speed, your velocity increases, which makes it quadratic. So here we have a diver jumps off a high platform with an initial vertical velocity of 16 feet per second. What equation represents the height of the diver after t seconds of the dive? Well, we're not given all that much information here. We're given two pieces. We have an initial vertical velocity of 16 feet per second, and we have an initial height of 30 feet. But that's still not a ton of information. What we need is an equation. What's nice about any vertical motion on the planet Earth is it follows the same equation. We have h of t equals negative 16t squared plus, and then this little v0, that's called v naught t plus h naught. And so what we have, h of t, this is the height at time t. The negative 16, this constant that's sitting right here, that's gravity. That's gravity in feet per second squared, would be the units there. Later on, when you're taking physics or something like that, you might have this same equation, but it has negative 9.8. That would be meters per second squared. We're sticking with feet for this lesson, but just know that that could change. If you were on a different planet with different gravity, that number would change. But for Earth, we've got negative 16t squared. Then plus, we've got this v naught, I called it. This is the velocity at time 0. That's what that little 0 is. It's the starting or the initial come on, pen, velocity. That little 0 means initial. And so this h0 or h naught is going to be the initial height. So that's, again, just the starting value. So all we need to make an equation for vertical motion is the initial velocity or the starting velocity and the initial height. So coming back to our problem, we have the initial velocity and we have the initial height. We just need to plug those in. H of t equals negative 16t squared plus the initial velocity was 16t, and then the initial height was 30 feet, so plus 30. Now the initial velocity does have to be in feet per second, and the initial height does have to be in feet, because this negative 16 is using feet in seconds. So if we wanted to change it to like inches instead of feet, then that negative 16 would have to change. So the initial height does need to be in feet, and the initial velocity is feet per second. So, but then we just plug it right into that equation. That's it. We've got the equation of the height of the diver after t seconds. Now, a lot of times it's going to ask another question: how many feet above the platform will the diver be at the highest point of the dive? Well, the feet above the platform, the highest point, it's going to be right up here. That's going to be at the vertex, right? So, how do we find the vertex? This is in standard form. We're going to do negative, the vertex is going to be at negative b over 2a. So we have to plug that in. That's the x value of the vertex. Will be at negative 16 over 2 times a, which is negative 16, which is 1/2. So x, or I guess in this case it would be t, because t is the variable we're using, equals 1/2. Let's plug 1/2 into the equation, h of 1/2. We've got negative 16 times 1/2 squared plus 16 times 1/2 plus 30. 1/2 squared is 1/4. Remember, it's just 1/2 times 1/2. You can square the top and square the bottom. We have 1/4 times negative 16 is negative 4 plus 8 plus 30. Negative 4 plus 8 is 4 plus 30 is 34. So h of 1/2 equals 34. So the height is 34 feet. That's not what the question is asking, though. How many feet above the platform will the diver be? Well, the platform is 30 feet tall. He gets up to 34 feet. That means he'll be 4 feet above the platform, which means he ended up jumping 4 feet which is impressive, I think. Next, we're going to assess a fit of a function by looking at the residuals. On the slide after this, I'll show you how to find residuals, and I'll define residuals here in just a second too. So, assessing the fit of a function. So if we have a function, how does that fit? So each year, for the past 5 years, ticket prices for the school play have increased by $1. The director used the function f of x equals negative 7x squared plus 90x plus 750 to represent the relationship between the number of price increases and the average predicted revenue per show. And then it's shown from the table. We'll see the table in just a second. How well does the function represent the actual revenue data? So, first thing we would do is we'd use the function to figure out what those values are by just plugging in our values, which would be the increase. Plug in 0, 1, 2, 3, and 4. What would we predict the revenue would be? Now the actual revenue, and this is the table values, this is what actually happened. From there, we can find the residuals. The residuals is going to be the actual minus the expected or predicted. It's the actual, so 745 minus 750. We just need to subtract these to find the residuals. So the residuals would be the error. Now, error is not necessarily a bad thing. Like, it doesn't mean mistake. Error is just the difference between what we predicted and what actually happened. When we make a model, it does not mean that everything is going to fit perfectly on the model. The model is a prediction. It generalizes things, but there's always going to be variation in what actually happens. So first thing, we just plug in the values to get those predicted values, and then we'd subtract to get the residuals. Second step, make a scatter plot of the data and graph the function on the same coordinate grid. Different ways you can do this. You can do this in a calculator. You can do this using Desmos. I'll show you that on the next slide. You can do it on paper, although on paper, if you were to do it, you'd plot your points for the predicted and then connect the dots as best as you can for those. But we can make our scatter plot and our prediction. It matches fairly well, right? We have some, like the points are all pretty close to the line. So what the residual is it's this vertical distance between the point and the line. When it's above the line, the residual is positive. When the point is below the line, the residual is negative. So we made a scatter plot so we could see what was going on. It looks like it matches fairly well. Next step, we can make a residual plot to show the fit of the function. A residual plot, you would use the same x value, and then the residuals would be your y value. What that does is it zooms it in. Like here, we're looking at 1,000. And so like these little differences could be pretty big. When we zoom it in, all of a sudden now we're just going from like -5 to 13. It's a much smaller spot. What are we looking for the residuals? We're looking for some positives, some negatives. We're looking for them to be scattered. Like we don't want to really see a pattern in the residuals. And so this one looks pretty scattered. We have some above the graph, some below the graph. And so assess the fit of the function using the residual plot. It shows the both positives and negatives, which means it's a pretty good model, which is also supported by looking at the graph itself. So that's looking at how we can see how well the residual plot fits. Now, how do we find that? And how do we find this? Like the teacher just is using this function. Well, this function didn't come out of nowhere. I mean, it fits pretty well, but where'd that function come from? Well, now that's what we're going to see here. We're going to fit a quadratic function to the data. So the theater director at the high school wants to get the most accurate quadratic model for the sales based on that previous example. How would the revenue be affected if the price is increased one more time? So what we can do is, first let's get the data. I don't remember the data from the previous slide. So here it is. These are the price increases and the actual revenue, because the predicted values from the equation that he used don't matter to this problem, because we're going to find an equation that might be better. And so how do we do this? We can do it using a calculator, which I can show you, but I know that few of you have a calculator. But what you do all have is access to Desmos, because it's a free online calculator. And honestly, the regression on it is really quite fantastic. And regression is the process of fitting a model to data. So you'd want to go to desmos.com, just click the graphing calculator link. We're going to put in a table. To enter a table, you'd click this little plus sign here, and it pulls up x1, y1, and then you just enter the table. Notice it's exactly like the table looks like. It'll pop up with dots on your graph, but notice the y values are really big, and so there's a little wrench icon right off the screen. cropped it so it would fit. There's a wrench icon, which you can adjust your screen, the window. I made mine from the x went from -1 to 10, and the y value I went from 0 to like 1300. So we can get those points. Now then in the second line, and this is how you do the regression, you do y1, because that's what this is called, y1. And to do the 1, by the way, you actually just type the letter y and then the number 1, and it'll put it in a subscript like it's supposed to be. And then you don't do equals. You do this little tilde deal, which is, it's like shift 1 gives you the exclamation point. It's the button to the left of 1. It's shift that. And then we have the equation in standard form. ax1 squared plus bx1 plus c. You just type it in, and then it gives you all of this stuff. All of that stuff just pops up, and the line comes up as well. So what does this tell you? This gives you the a, b, and c that go into the equation. So our equation is y equals -8x squared plus 95.2 x plus 749.8. That's the equation it gives us. If we wanted to find residuals, so before we get to residuals, this r squared, the closer it is to 1, the better of a fit it is. This r squared is 0.9935. That means that this is a really good fit. And then over here, it says residuals. And then E1, that would be error 1. And then there's a little thing that says plot. If you click that little plot, what'll happen is it'll calculate all those residuals for you. And it puts it in the table right next to the y1 values. So you have all those residuals. It also graphs them for you, but these are all in the -11.4 to 9 range, which is way below this on the thing. So you'd want to change the y values of your, you'd want to change the y values of the graph so that you can actually see this. Because right now, even if I hadn't cropped it out, they just all look like they're sitting on the axis at 0. So you'd want to zoom in on the y values. And then we have the last part of the question. How would the revenue be affected if the price increased one more time? So basically, we want to find what is that value. Notice we have this value here. There's a little dot there. It's kind of grayed out because it's not one of our points. That's the vertex. If you hover your mouse over it, it will give you that point. It's like 5.95 comma something. But we don't need to find the vertex for this problem. If you did, though, it's right there. We want to find this point. This is when we want to find the point when x equals 5. Well, we can just plug 5 into this equation, but when we do it, I mean, it's a little bit ugly, and it could be a lot uglier than that. So, being that we're already using a calculator, we could continue using a calculator. We could continue using Desmos. How would you plug 5 in? Well, you could just plug 5 in, or when you write the equation, you can type it into the next line, but when you do it, instead of y, use function notation, use f of x. because if you plug in f of x equals the equation, the next line, you just do f of 5, and it gives you the answer. So if we increased it by another $1, our revenue would be $1,025.80. Now, 6, if we increase it again, that would be a little bit higher. But after that, it's going to start going down because it's going to get past the vertex. You might wonder, like, how does that work? If you keep increasing ticket prices, wouldn't the revenue keep going up? No, because if you keep increasing ticket prices, eventually fewer and fewer people are going to come to see the show. And I mean, if the ticket prices were all like $300, you're going to get not many people coming to see the show. And so you're not going to sell many tickets. And so that goes down. So that's how that generally works. So this is looking at modeling real-world data using quadratic models. We've got area, we've got vertical velocity, and then we've got residuals and regression and how to do it, probably using Desmos. If you have a calculator, I can show you how to do it on your calculator as well. Just ask. But until then, I will see you in class. Until then, keep working problems, keep asking questions, and as always, happy mathing.